last classes we were in the middle of this theorem by Rasborov about the hardness of a clique problem for monotone circuits. So we basically, the proof strategy was to convert any monotone circuit that solves the clique problem on these two distributions that we had defined, the yes distribution, the no distribution. Any such monotone circuit, we will convert it into these clique indicators, few clique indicators. Okay, so as long as the monotone circuit is small, it is smaller than n to the square root k by 20, we can actually collapse it into an OR of clique indicators. And on the other hand, we had shown that for these distributions, clique indicator cannot solve the problem. Okay, so that is how we showed that monotone circuits will be large. While we converted these AND OR gates in the monotone circuit, when we convert AND OR gates to this OR of clique indicators, we employed sunflower lemma. So today we have to finish that proof. So the sunflower lemma said that it talked about the existence of a sunflower, right? Basically a collection of sets or subsets that have the same mutual intersection. So Z is a collection of sets of size at most L. It says that as long as you have a lot of sets, so more than p minus 1 to the L times L factorial. Okay, so exponential in L. If you have exponential in L many subsets, then what happens is there is a sunflower. So then you will have these P subsets forming a sunflower. That is, for every pair ij, the intersection is Z. Okay, for some subset. This subset Z may not be in the collection, it is just something in the universe. So there exists a Z such that this thing is true for every pair. So we have to basically somehow use this condition in the proof. So the way we will use it is, we will do induction on L. Okay, so for this expression with L minus 1, suppose you have a proof, then we will show it for L. So the idea is induct on L, so let us first look at the base case. What happens when L is 1? When L is 1, then you are saying that there are at least P subsets, and moreover their sizes, each of them has size only 1, right? These are singletons. So obviously, I mean, if they are singletons and they are distinct, then the mutual intersection is empty, they are disjoint. Which means that Z1 to Zp in Z form a sunflower. Notice that we never said that intersection will be non-empty. We just want in a sunflower the intersection to be the same. It can also be empty, in this case it will be. So Z has collection, this fancy Z collection has at least P subsets, singletons, you pick them, that's a sunflower. So that case is done. Now let us move to the induction step, which is L greater than 1. So here this taking a cue from the base case, let us first try to collect disjoint subsets. So let M be a maximal collection of mutually disjoint sets in Z. Okay, so maximal means that if you take any extra set and put it in M, then there will be an intersection with something already in M. Okay, so collect as many disjoint sets as you can. If you already have P, then you are done. So we are then in the case M less than P. So what do you do in this case? So you don't have enough disjoint sets. So now whatever you will add, it will intersect, overlap. So in this case, look at the union of all the sets in M. How many elements will you get? So this will be M has at most P minus 1 sets, each of size at most L, so P minus 1 times L. Also, second property is that I already said that for every subset in the collection fancy Z, this set Z will intersect with something in M. So in the union of M, there is some intersection. It's non-empty. Right? So this means that there exists an X in the union of the sets in M. So note that M has at most P minus 1 sets. So first let us look at the frequency of X. So there is an X appearing in S many sets in Z, say Z1 to Zs, where S, I want this X to appear in many subsets in M. Okay, I want to maximize this. So what can I say about S? How big can I choose it? So how many X's are there? So let us first look at this equation 1 and this equation 2. So from equations 1 and 2, from 2 you get that in the union of M there is an element, or the other way. So every subset in the collection Z will contain some element from union of M. So how many subsets are there? These many subsets are there, right? Size of this fancy Z. And how many elements are there in union of M? That is at most P minus 1 by L by equation 1. So what I want to say is this ratio, if you look at size of Z divided by the number of elements, so number of subsets divided by the number of elements in union of M, there is some element which appears in that many sets. Okay, so there is actually so we are basically doing an averaging argument by which we can say that if you look at this ratio of Z, number of sets divided by number of elements, there is some element which appears in so many sets, because if that is not the case, if every element appears in fewer than these, then what you will get is a contradiction. Okay, then you will be contradicting equation 2. So equations 1 and 2 imply this, because equation 2 is saying that every subset has to intersect, right? So some element X in union of M has to appear a lot in many subsets. Now what is S? So S is greater than equal to the size of Z we have pegged to be P minus 1 to the L times L factorial divided by P minus 1 times L, which is equal to P minus 1 to the L minus 1 times L minus 1 factorial. So this expression is familiar. This is the same expression if L was L minus 1. Okay, so in the previous induction hypothesis, you can say that is the expression. So, but how do we invoke the induction hypothesis? So the way we will do it is that we will actually look at those sets where X appears. So we will find a sunflower in Z1 to Zs. That's the idea. So apply induction hypothesis on Z1 minus X dot dot Zs minus X. Okay, so these are subsets whose size is L minus 1 or less, and S is at least P minus 1 to the L minus 1 times L minus 1 factorial. So you can use induction hypothesis, and what you will get is there exists a sunflower. So let me call this Z prime. There exists a sunflower in Z prime, which means that P subsets are here with the same intersection. So if you bring X back, the intersection will still remain the same. So it's a sunflower in Z. Okay, that finishes the inductive proof. So we did the base case and we did the case where M is not large enough, it's P minus 1 or less. Right? So the idea was that then union of M will have fewer elements, and you can use induction hypothesis by removing this element X. So this finishes Rasborov's theorem. Right? We finished this theorem that we started many lectures back, that for k n to the 1 by 4, any monotone circuit solving k clique will require this n to the square root k sized monotone circuit. Okay, that was a long proof. So this sunflower lemma itself is actually a very interesting combinatorial fact. And one open question I can state. So, what is open is the sunflower conjecture. It says that this bound that you had, L factorial, this can be slightly reduced. It can be reduced to, let us say, 2 to the L, okay, or some constant to the L. So, whether this bound is optimal or not, can you reduce this bound? So, specific conjecture is that the L factorial can be reduced to C to the L. Okay, this is called the sunflower conjecture. It's still open. And one interesting thing is that this conjecture actually appears in some other problems. For example, it appears in matrix multiplication algorithm. Okay, so if you can prove this, then there are these tricks by which you can do faster matrix multiplication. So if somebody wants to read this as an advanced topic, they are welcome. Okay, so at this point now we will change the topic kind of drastically. Okay, so from proving lower bounds for these restricted circuit models, we will now move to pseudo-random constructions. So one aspect of this course, as we had advertised, is that we will try to construct these mathematical objects which have pseudo-random properties. So the first example of that phenomena that we will see is in the area of graph theory, specifically called spectral graph theory, and the topic is expanders. Okay, so we will do expanders now. So this will be the first topic. In our list of pseudo-random constructions. So this may not be clear what is the meaning of precise meaning of pseudo-random object or pseudo-random construction, but here you can think of properties of a randomly chosen graph. So one property that you can show a random graph has is that the connectivity is very high. So if there are n vertices, then you can reach from any vertex S to any vertex T in short paths. Okay, so that kind of a property we want in an explicitly constructed graph. Okay, we want a highly connected, well connected graph and explicitly constructed. So graph families, construct a graph family that is very well connected. So not only you can reach from any vertex to any vertex, but you can actually reach in very few steps. Okay, so for n vertices, instead of the distance being n, the distance will only be log n, let's say. So in terms of vertices, it will be logarithmic distance or diameter. Okay, that is just one property. So we will want to construct such graphs. These are highly useful graphs. They are also useful in practice, and they have great applications in proving theorems. Okay, even unrelated problems, so sometimes expanders are used. So one such application is already in graph theory, where expanders are used, or the concept of expansion. The concept of expansion is used. So we can call this application number 1. This is the major application. We want to solve the problem of undirected graph connectivity in log space. So given a graph, in the Turing machine, the work tape will only have log n or order log n space, only those many cells will be used. And just by log n, order log n space, you want to decide whether there is a path from S to T. Okay, you want to solve the connectivity problem. Now note that the number of paths can be like n factorial, or at least 2 raised to n, right? Number of paths can be exponential. So you cannot just blindly or by brute force search the space of paths. You have to be more systematic. In particular, if your graph already had diameter log n, then maybe you can come up with a brute force algorithm, and then you can solve the problem in log space. But what if your graph was not well connected? The diameter was much bigger than log n, right? So how do you solve those connectivity problems on those input instances? So that's a major, in fact, area in computer science. And in the end of this study on expansion, we'll solve this problem completely. Okay, you will see a solution. So first we will start with RL. RL is basically a randomized log space algorithm. Okay, this will be much easier, and once we have developed this area enough, then we will show that actually it can be de-randomized. So this will be a de-randomized version. So we will do random first, and then we will de-randomize the randomized algorithm. So let's define the problem formally. So this U path, the input instance is graph, source vertex, target vertex, G comma S comma T, such that there is a path. From S to T in the undirected graph G. Okay, so this is the language, and the decision problem is whether a given input instance is in this set in this language or not, right. That is how we have modeled our problem. And now comes the main attraction, which is that well, first of all, U-path in practice is a very easy problem, right. Connectivity you can solve by doing a depth first search. So you can solve it in linear time. So that is not an issue. It's obvious that U-path is in P, right. You can solve it in fact in linear time, that is not the issue, but you want to solve it much better than polynomial time. So this major non-trivial algorithm for U-path was given by L.A. Leunas, Karp, Lipton, Lovash, and Rakoff. It's quite old, 1979. So this AK-LLR algorithm puts, it's a randomized algorithm, it puts U-path in RL, okay, randomized log space. So imagine that you are given a map of a city, right, and then you want to move from place S to place T. So obviously the map of a city can be very large, right. You don't want to remember the whole map, but you can pick any point in the map and then you can look at the adjoining locations basically connected by a street, right, and then you can start moving on a street, go to another location, from there again pick a street, go to a third location, and so on. So the same thing, can you simulate this thing by using very little space? Okay, so your workspace is very small, you cannot store the whole map. You can only look at local neighborhood in the map and make decisions based on the local neighborhood, not the global information or the global map. So this theorem says that yes, that can be done. So how is that possible? Right, this seems impossible. How can you not store the whole map and just based on very local decisions solve this global problem? So this will be the starting point of spectral graph theory. So we'll basically simulate this walk on an undirected graph. We'll simulate this walk as a matrix multiplication problem. Okay, look at the adjacency matrix. So consider adjacency matrix. And simulate a random walk on graph G as matrix multiplication or matrix powering. Okay, kind of multiplying by matrix A, then multiplying A again, so A square, A cube. So basically you want to start from your vertex S and then randomly make choices of neighbors and keep on walking, and this simulate this as if you are multiplying by this adjacency matrix, a vector. Okay, and then after you have done this for a long time, study where you reach. Okay, so basically, what is the probability of reaching vertex T in, let's say, L steps? That is the analysis we want to do. So, matrix analysis and probability. Okay, this is a very, the tools here will be very interesting. So, let's start that. So, suppose G is the given undirected graph with n vertices. So, first what we will do is, in the matrix analysis part or in this random walk analysis part, we will need this graph to have a special property. So, basically the property we want is, at whenever we are at a vertex, the number of choices should be constant, it should be fixed, and it should not change. Okay, so in other words, the degree of the graph, every vertex should be the same. So we want, we need G to be regular. That is for all vertices, degree of V is D. Okay, so we want every vertex to have the same degree. So obviously the input graph may not have this property, so we will transform the graph. Again, we have to transform it in a log space way. So example, we can transform G to get D equal to 3. Why is that? Okay, let us just see this in a picture. So suppose you have a vertex V with 5 neighbors. So then we can add more vertices and achieve degree 3 everywhere. How do you do that? So let's make 3 copies, or let's create these vertices, different vertices V, V prime and V prime prime, and V is connected to U1, U2, and V is also connected to V prime, and V prime is connected to V prime prime. So V now already has degree 3, right? So let's now move to V prime. So give U3 to this, and also U. So now degree of V prime is 3, and degree of V prime prime can be made 3 by adding U4, U5. Okay, so let's say these copies of V, V prime and V prime prime, these have degree 3. Okay, so at least this vertex we have made degree 3, and then on the other vertices you do the same trick. So apply this gadget on all the vertices, and for this you don't need global information, you only need information about the neighbors. So this can be done in log space. Why? Because the neighbors are at most n, right? So you can actually access the neighbors just by their indices, which will only require log n space. This can be done in log space. Okay, so in terms of vertices n, or even the edges, which can only be n square, in log of that, that much space is enough. And so G can be transformed to a new graph, which can be written on an output tape. Work tape is only log n space. So what we have done is, so now on, assume G to be 3 regular. Okay, so we can now assume G to be D regular, where D we can even pick 3. Notice that we cannot manage this in D equal to 2. Okay, 3 is the minimum. Now the algorithm is, as suggested before, a random walk. So the question is how long the random walk will be. How many steps do you have to take? So on this we do a random walk. Starting from some vertex S of length times n to the 4 log n. So don't worry too much about these factors, just focus on n to the 4. So what we are saying is that we'll take random steps around n to the 4 many times, starting from S. Okay, and the claim is that if T is connected to S, then we will reach it. Okay, so by a random walk, we can reach T in these many steps with a high probability. And since it's a random walk, it doesn't need global information. Okay, we'll only look at the neighbors. Right, since the length is n to the 4, again when you want to count the steps, you only need a log of that many, so log of n to the 4 many bits. So overall everything you can simulate or implement in log n space. Okay, so this is definitely a log space algorithm. The only question left is what is the error probability or what is the success probability. Also assume G to have self loops. So which means that so for every vertex V, we need this edge V comma V. Okay, so these self loops are also present. This obviously won't change the connectivity, right? So if S to T was connected, then it will remain connected. So we just throw in these self loops also. This will help in the analysis. It may not be clear why, but somehow it will. So in the end, you will understand why self loops were added. And now comes an important definition that of the adjacency matrix, but we will use a normalized version. So let A be the normalized adjacency matrix. They have great applications in proving theorems. Okay, even unrelated problems, so sometimes expanders are used. Of G. By that we mean every entry Aij. So either it is, I mean either Ij is an edge or it is not, right? So either it is 0 or 1, but you also normalize it by the degree. So degree normalized adjacency matrix. So we can write it as number of edges from I to j divided by d. Okay, so there are fractions, either 0 or 1 by d, which is 1/3 actually. So either 0 or 1/3. And since this was a, I mean there were these self loops, so in the diagonal you will have 1 by d. And since it is undirected, it's a symmetric matrix. So these are the simple observations. Let's note them down anyways. For all I 1 to n, Aii is 1 by d because of the self loops. A is symmetric. With entries 0 or 1 by d, and finally the row sum and column sum is 1. Okay, so this is the reason why we normalized it, because when you look at a row, so ith row, basically how many neighbors does I have, that is d, exactly d. So when you normalize, you get the row sum 1. Okay, so these matrix in matrix analysis are called stochastic. So A is symmetric stochastic matrix. Okay, that's the property of A, symmetric and it is stochastic. And the entries are not arbitrary, actually the entries are also very special, they are just 0 or 1 by d, non-negative entries but very special. So this is an n by n matrix. So we promised that, or we suggested that we will think of this matrix as a transformation matrix, right? So what is it transforming? So it will transform, or we will view this as transforming the probability vector. Okay, so for the ith vertex there is a probability of u being there at any point of time in the algorithm. So at any time there is a vector of probabilities, right? There are n probabilities, their sum is 1 because you will be at least somewhere, so the sum will be exactly 1, and that vector this matrix transforms as you do as the random walk proceeds. So E transforms the probability vector So, we will prove this formally. Right now it is only an idea, okay, just remember this idea. Calculations we will do next. So, think of A as transforming the probability vector P bar. So, P1 to Pn, think of it as a column vector. Where Pi is the probability of being at vertex I. Okay, that is the idea. That is how we will think of this matrix. So, at any stage of the random walk, this sigma Pi equals 1, and initially Pi is 1 for I equal to S, because S was the source vertex where you were initially, and 0 otherwise. Right. So, initially P bar was this Sth elementary vector, and then as you move forward, as you do the random walk, the probability will kind of distribute. From S it will go to its neighbors, then to neighbors of neighbors, and so on. As your network grows, the probability spreads to other vertices, and ultimately after many steps of the random walk, you might have a decent probability of being everywhere, right. So, that is what we will prove. This probability vector P bar, we have to now study how it will change in one step. So, that is the key property which will help you understand or help you see matrix A as a transformation of probabilities, or even a matrix of probabilities. So, in one step of the random walk, the probability changes as So, P bar will become probability vector Q bar A times P bar. Okay, so, the transformation is very simple, you just multiply with the matrix, that is one step. Once you see this, the proof is quite easy. So, by definition, Qi is the probability of the walk being at vertex I. Now, if you are at I now, then in the previous step you were at some other j, and you have to look at the probability of reaching I from j in one step, right. So, that is a sum over probabilities. So, probability of walk at I given that previous was j, let's say. Times the probability that previous was j. And j is over all the vertices, so 1 to n, right. So this is what so probability of previous being j, that is p bar given by p bar, right. So the jth coordinate pj. Let me maybe do it in this order. So probability that the walk is at I coming from j, that probability is j to I, right. Now in a random walk you will pick a neighbor with equal probability. So only if j to I there is an edge, right. So that probability is exactly given by the matrix entry. So matrix entry is AJI times the probability that previously you were at j, which is Pj. Now remember that Gi is Ij by symmetry. So what is this? This is the inner product of two vectors, the ith row vector and the probability vector p bar, right. So we can write it as A times p bar its ith entry, right. This is the same as the inner product of ith row of A with p bar. So this is true for every I, right, which means that q bar is AP bar. Right, so that is one step. Now once you understand one step, you understand a lot more because every step is matrix multiplication. So 2 steps is A square times p bar, L steps is A to the L times p bar. So if you if you call the first probability vector to be E bar S, be the elementary vector with 1 at the sth coordinate and others 0, then you can write that after L steps of the random walk, the probability vector is E to the L times E bar S. Okay, so just multiplication or powering of A L times L fold powering. So the question that remains now is what is the Tth entry of this? right? Remember, because our original goal is to understand the randomized algorithm we gave, that after L steps of the random walk, starting from S, will you reach T with what success probability, right? That is what we want to answer. So what is AL? What is the probability of reaching T in L random steps? So how large is this, right? That is what we want to understand. How large or how small? Is this a decent probability? So for example, if this probability was 60%, it's a good chance of reaching T, right? So the question is this probability 60%, 80%, or is it just a very small probability, exponentially low probability? Right? Anything can happen because the number of paths is too high. The number of paths is at least 2 raised to n. Your graph was a general graph. So the probability can also be 1 over 2 raised to n. So is it that small or is it much bigger? So this is what we will analyze. We will not be able to finish this today, but next time we will finish this analysis. So the main tool now will be to understand this A raised to L, we have to move to its eigenvalues, okay, and then everything will become a study of eigenvalues of the matrix A, and hence A to the L. So study the magnitude by using the eigenvalues of A as the main tool. Okay, so eigenvalues, and when you study eigenvalues, obviously eigenvectors as well appear. So what is the meaning of this? So recall that an eigenvalue is lambda, an eigenvector is V, if the action of A on V is simple, it is just scaling by lambda. So this is the meaning of eigenvalue and eigenvector. It basically reduces the study from a matrix to a number. Okay, lambda is simply a complex number. In this case, what happens in our case, because of the symmetric nature of the matrix A, the eigenvalues are all real. So I will leave this as an exercise. Symmetric and stochastic. So symmetric stochastic A implies that eigenvalues are real so eigenvalues lambda 1 to lambda n. There are n eigenvalues, possibly with multiplicity, are real, and if you order them by their unsigned value, So smallest magnitude is lambda n, then it is lambda n minus 1, then lambda 1. So the largest value is 1. Okay, exactly 1. So prove this as an exercise. So the eigenvalues are actually real and the maximum is 1. Okay, and based on this, now we'll analyze a to the l's action.